Using 600 volts current transformers for 13.2 kV and 5 kV applications is not recommended, and it is likely not compliant with electrical codes and safety standards. Here are the reasons why. Firstly, safety concerns. 600 volts current transformers are not designed to handle the higher voltages present in 13.2 kV and 5 kV systems. Using current transformers rated for a low voltage can lead to insulation breakdown, arcing, and potential hazards to personnel. Secondly, code compliance. Electrical codes and standards such as the National Electrical Code and the Institute of Electrical and Electronics Engineers standards specify specific requirements for the use of current transformers, including voltage ratings. Using current transformers with an incorrect voltage rating is a violation of these codes and standards. Thirdly, accuracy and reliability. 600 volts current transformers will not provide accurate readings for 13.2 kV and 5 kV applications. Incorrect current transformer ratios can lead to inaccurate metering, protection, and control systems. This can result in unreliable system operation and potential safety issues. The correct solution is to replace the incorrect current transformers with current transformers that are designed for the appropriate voltage levels. This will ensure compliance with codes, provide accurate readings, and minimize safety risks. If it is not immediately possible to replace the incorrect current transformers, there may be some temporary or limited use alternatives to consider. 1. Use portable current transformers with the correct voltage rating. 2. Install Rogowski coils around the conductors. These are non-invasive devices that can provide current readings without requiring direct contact with the conductors. 3. Ensure that the 600 volts current transformers are used with proper caution, with clear labeling and safety measures in place to minimize potential risks. However, it is important to emphasize that these alternatives should only be considered as temporary solutions until the correct current transformers can be installed. Current transformers, or CTs, are a type of transformer used to measure alternating current. They are designed to produce a current in their secondary which is proportional to the current in their primary. Current transformers are used extensively for measuring current and monitoring the operation of the power grid. They are typically used in applications where the current to be measured is too high to be directly measured by an ammeter. The current transformer isolates measurement, protection, and control circuitry from high voltage or high current primary circuits. Current transformer has a primary winding, a core, and a secondary winding. The primary winding is connected in series with the conductor carrying the current to be measured. The secondary winding is connected to an ammeter or other measuring device. The core is made of a ferromagnetic material such as iron or steel, which provides a path for the magnetic flux produced by the primary current. The current in the secondary winding is proportional to the current in the primary winding, with the ratio of the two currents being determined by the turns ratio of the transformer. For example, a current transformer with a turns ratio of 100:1 will produce a secondary current of 1 amp for every 100 amps of primary current. Current transformers are typically specified by their current ratio, burden, accuracy class, and voltage rating. The current ratio is the ratio of the primary current to the secondary current. The burden is the impedance of the measuring device connected to the secondary winding. The accuracy class is a measure of the accuracy of the current transformer expressed as a percentage of the primary current. The voltage rating is the maximum voltage that the current transformer can withstand without insulation breakdown. There are several different types of current transformers, including window type, wound type, and bushing type. Window type current transformers have a hollow core through which the conductor carrying the current to be measured is passed. Wound-type current transformers have a primary winding that is wound around the core. Bushing-type current transformers are designed to be mounted on bushings, which are used to insulate conductors as they pass through grounded enclosures. When selecting a current transformer, it is important to consider the application, the current to be measured, the accuracy required, and the voltage rating. It is also important to ensure that the current transformer is properly installed and maintained to ensure accurate and reliable operation. The National Electrical Code, or NEC, provides guidelines and regulations for the safe installation of electrical wiring and equipment. Article 310.15 of the NEC covers the ampacity of conductors, which is the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. This section of the NEC provides tables and formulas for determining the ampacity of conductors based on factors such as conductor size, insulation type, ambient temperature, and the number of conductors in a raceway or cable. The NEC also addresses the use of current transformers in various sections. For example, Section 450.3 addresses the overcurrent protection of transformers, including current transformers. This section specifies the requirements for overcurrent protection devices such as fuses and circuit breakers to protect transformers from damage due to overloads or short circuits. Section 314.27 addresses the use of outlet boxes and fittings in electrical installations. This section specifies the requirements for the size and type of outlet boxes and fittings to be used in different applications, including those involving current transformers. Section 392.10 addresses cable trays, which are used to support and route cables in electrical installations. This section specifies the requirements for the construction, installation, and grounding of cable trays, including those used to support cables connected to current transformers. The Institute of Electrical and Electronics Engineers, or IEE, is a professional organization that develops standards for a wide range of electrical and electronic technologies, including power systems. IEE standards related to current transformers include IEC 57.13, which covers the requirements for instrument transformers, including current transformers. This standard specifies the performance requirements, testing procedures, and safety requirements for current transformers used in power systems. IEC 37.110 covers the application of current transformers used for protective relaying. This standard provides guidance on the selection, application, and testing of current transformers used in protective relaying systems, which are used to detect and isolate faults in power systems. IEE 80 covers the grounding of electrical systems. This standard provides guidance on the design, installation, and testing of grounding systems for electrical systems, including those that use current transformers. These IEE standards are widely recognized and used in the power industry to ensure the safe and reliable operation of electrical systems that use current transformers. Rogowski coils are a type of current transducer that can be used to measure alternating current. They are non-invasive devices that do not require direct contact with the conductor carrying the current to be measured. Rogowski coils consist of a helical coil of wire that is wrapped around the conductor. The coil is typically air-cored, which means that it does not have a ferromagnetic core. When an alternating current flows through the conductor, it produces a magnetic field that induces a voltage in the Rogowski coil. The voltage induced in the coil is proportional to the rate of change of the current in the conductor. The output voltage of the Rogowski coil is typically processed by an integrator circuit, which converts the voltage signal to a current signal that is proportional to the current in the conductor. Rogowski coils offer several advantages over traditional current transformers. Firstly, they are non-invasive, which means that they do not require the conductor to be interrupted or disconnected. Secondly, they can measure a wide range of currents from very low currents to very high currents. Thirdly, they are immune to saturation effects, which can occur in current transformers with ferromagnetic cores. Fourthly, they are lightweight and flexible, which makes them easy to install in tight spaces. Rogowski coils are used in a variety of applications, including power monitoring, harmonic analysis, and fault detection. They are also used in applications where high accuracy and wide bandwidth are required. When using Rogowski coils, it is important to ensure that they are properly calibrated and that the integrator circuit is properly designed. It is also important to ensure that the coil is properly positioned around the conductor to minimize errors. The voltage rating of a current transformer is the maximum voltage that the current transformer can withstand without insulation breakdown. The voltage rating is typically specified in volts. The voltage rating of a current transformer is determined by the insulation material used in the transformer and the spacing between the windings and the core. It is important to select a current transformer with a voltage rating that is appropriate for the application. If the voltage rating of the current transformer is too low, the insulation may break down, which can lead to arcing and potential hazards to personnel. If the voltage rating of the current transformer is too high, the transformer may be more expensive and larger than necessary. When selecting a current transformer, it is important to consider the maximum voltage that the transformer will be exposed to in the application. This includes the normal operating voltage, as well as any transient voltages that may occur due to switching or lightning strikes. It is also important to consider the altitude at which the current transformer will be used. The voltage rating of a current transformer decreases with increasing altitude due to the lower dielectric strength of air at higher altitudes. If a current transformer is to be used at a high altitude, it may be necessary to select a transformer with a high voltage rating. Proper labeling and safety measures are essential when using electrical equipment, especially in high voltage applications. Clear labeling helps to identify the equipment and its voltage rating, which is important for preventing accidental contact with high voltage conductors. Labels should be durable and clearly visible, and they should be placed in a location where they can be easily read. Safety measures help to protect personnel from electrical hazards. These measures may include the use of insulated tools, personal protective equipment, and lockout-tagout procedures. Insulated tools are designed to prevent electrical shock. They are typically made of a non-conductive material, such as rubber or plastic, and they are rated for a specific voltage. Personal protective equipment, or PPE, includes items such as gloves, safety glasses, and arc flash suits. PPE helps to protect personnel from electrical hazards such as electric shock, arc flash, and arc blast. Lockout-tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. In addition to these general safety measures, there are also specific safety measures that should be taken when working with current transformers. These measures include ensuring that the current transformer is properly grounded, avoiding contact with the current transformer while it is energized, and using a current transformer with the correct voltage rating for the application. By following these safety measures, it is possible to minimize the risks associated with working with current transformers and other electrical equipment. Using current transformers with an incorrect voltage rating is a violation of electrical codes and standards, such as the National Electrical Code and the Institute of Electrical and Electronics Engineers standards. These codes and standards specify the requirements for the use of current transformers, including voltage ratings, to ensure the safe and reliable operation of electrical systems. Violating these codes and standards can result in fines, penalties, and potential liability for damages caused by electrical accidents. In addition to the legal consequences, using current transformers with an incorrect voltage rating can also have serious safety consequences. As mentioned earlier, using current transformers rated for a lower voltage than the system voltage can lead to insulation breakdown, arcing, and potential hazards to personnel. It can also lead to inaccurate readings, which can result in unreliable system operation and potential safety issues. Therefore, it is essential to ensure that current transformers are used with the correct voltage rating and that all applicable electrical codes and standards are followed. If there is any doubt about the correct voltage rating for a current transformer, it is best to consult with a qualified electrical engineer or electrician. Insulation breakdown occurs when the insulation material surrounding a conductor or electrical component is subjected to a voltage that is higher than its dielectric strength. The dielectric strength of an insulation material is the maximum voltage that it can withstand without breaking down and allowing current to flow through it. When insulation breakdown occurs, it can create a conductive path through the insulation, which can lead to arcing and potential hazards to personnel. Insulation breakdown can be caused by several factors, including overvoltage, contamination, and aging. Overvoltage occurs when the voltage applied to the insulation material exceeds its dielectric strength. This can be caused by switching surges, lightning strikes, or other transient events. Contamination can reduce the dielectric strength of insulation materials. Contaminants such as dust, moisture, and chemicals can create conductive paths on the surface of the insulation, which can lead to insulation breakdown. Aging can also reduce the dielectric strength of insulation materials. Over time, insulation materials can degrade due to heat, moisture, and other environmental factors, which can make them more susceptible to insulation breakdown. To prevent insulation breakdown, it is important to select insulation materials with a dielectric strength that is appropriate for the application. It is also important to keep insulation materials clean and dry, and to protect them from environmental factors that can cause them to degrade. Regular inspection and testing of insulation materials can also help to identify potential problems before they lead to insulation breakdown. Arcing is a phenomenon that occurs when an electrical current flows through a gas, such as air, between two conductors. Arcing can occur when the voltage between the conductors is high enough to ionize the gas, creating a conductive plasma. The plasma can then conduct electricity between the conductors, creating a bright flash of light and a loud noise. Arcing can be caused by several factors, including insulation breakdown, loose connections, and corrosion. Insulation breakdown can create a conductive path between conductors, which can lead to arcing. Loose connections can create a high resistance point in the circuit, which can cause the voltage to increase and lead to arcing. Corrosion can also create a high resistance point in the circuit, which can cause the voltage to increase and lead to arcing. Arcing can be dangerous because it can generate high temperatures, which can cause fires or explosions. It can also generate ultraviolet radiation, which can damage the eyes. To prevent arcing, it is important to ensure that all electrical connections are tight and corrosion-free. It is also important to protect electrical equipment from moisture and other contaminants. Regular inspection and maintenance of electrical equipment can help to identify and correct potential problems before they lead to arcing. There are various alternatives to consider when you are unable to replace and correct current transformers. One is to use portable current transformers. Portable current transformers are designed to be easily installed and removed from conductors. They typically have a split core design, which allows them to be installed without interrupting the current flow. Portable current transformers are available in a variety of sizes and current ratios, making them suitable for a wide range of applications. When using portable current transformers, it is important to ensure that they are properly installed and that the connections are tight. It is also important to ensure that the current transformer is properly grounded to prevent electrical shock. Another alternative is to install Rogowski coils. As mentioned previously, Rogowski coils are non-invasive current transducers that do not require direct contact with the conductor. They are easy to install and can measure a wide range of currents. When using Rogowski coils, it is important to ensure that they are properly calibrated and that the integrator circuit is properly designed. A third alternative is to use the 600 volts current transformers, but with proper caution. If it is not possible to replace the incorrect current transformers or to use portable current transformers or Rogowski coils, it may be necessary to use the 600 volts current transformers with proper caution. This should only be considered as a temporary solution until the correct current transformers can be installed. When using 600 volts current transformers in high voltage applications, it is important to take extra precautions to minimize the risk of electrical shock. These precautions may include using insulated tools, wearing personal protective equipment, and isolating the current transformer from ground. It is also important to label the current transformer clearly to indicate that it is not rated for the system voltage. By following these precautions, it is possible to use 600 volts current transformers in high voltage applications with minimal risk of electrical shock. Using clear labeling is crucial for high voltage electrical systems. Proper identification helps prevent accidents and ensures safety. Labels should clearly state voltage levels and equipment functions. This allows personnel to quickly recognize potential hazards. Labels should be durable and easy to read. They should withstand harsh environments and remain legible over time. In addition to voltage and function, labels should include warnings. Common warnings include danger, high voltage, and authorized personnel only. These warnings reinforce safety protocols. Regularly inspect labels to ensure they are intact. Replace any damaged or missing labels immediately. Training personnel on label recognition is essential. Everyone working near high voltage equipment should understand the labels. Consistent labeling practices create a safer work environment. They reduce the risk of electrical incidents and improve overall safety. Implementing a comprehensive labeling system is a best practice. It demonstrates a commitment to safety and protects personnel. This dedication to safety is paramount in high voltage environments. Clear labels are a fundamental part of a strong safety program. By prioritizing labeling, you enhance safety and compliance. Safety measures are critical for high voltage environments. These measures protect personnel from electrical hazards. Always use insulated tools when working with high voltage equipment. Insulated tools prevent electric shock. Wear appropriate personal protective equipment (PPE). PPE includes gloves, eye protection, and arc flash suits. Maintain a safe distance from energized equipment. Never approach high voltage conductors without proper training. Implement lockout-tagout procedures to de-energize equipment. Lockout-tagout prevents accidental energization. Ensure proper grounding of all equipment. Grounding provides a path for fault current. Regularly inspect equipment for damage or wear. Damaged equipment poses a significant risk. Provide comprehensive safety training to all personnel. Training should cover hazard identification and safe work practices. Establish clear communication protocols. Effective communication is essential during high voltage work. Conduct regular safety audits to identify potential hazards. Address any identified hazards promptly. Follow all applicable safety regulations and standards. Compliance is mandatory for high voltage work. Promote a strong safety culture within the organization. A strong safety culture encourages safe behavior. By implementing these safety measures, you minimize risks. You create a safer working environment for everyone. Safety should always be the top priority in high voltage environment. A commitment to safety protects lives and prevents accidents. Accurate readings are essential for reliable system operation. Incorrect readings can lead to various problems. Inaccurate metering can result in billing errors. Customers may be overcharged or undercharged. Protection systems rely on accurate current transformer ratios. Incorrect ratios can cause malfunctions. Control systems use current transformer data for automation. Inaccurate data can lead to improper control actions. Unreliable system operation can cause equipment damage. Overloads or faults may go undetected. Potential safety issues can arise from inaccurate readings. Hazards may not be recognized in time. To ensure accurate readings, use correctly rated current transformers. Verify the current transformer ratio before installation. Calibrate current transformers regularly. Use high-quality metering equipment. Implement a robust data validation process. Monitor system performance closely. Investigate any discrepancies promptly. Provide training on meter reading and data interpretation. Foster a culture of accuracy and attention to detail. By prioritizing accurate readings, you improve system reliability. You also enhance safety and customer satisfaction. Accuracy is a cornerstone of reliable electrical systems. Without it, the entire system is compromised. Compliance with codes is essential for electrical installations. Codes ensure safety and prevent hazards. The National Electrical Code, NEC, is widely adopted. Compliance with the NEC is mandatory in many jurisdictions. Electrical codes cover various aspects of installations. This includes wiring, grounding, and equipment placement. Codes specify minimum safety standards. These standards protect people and property. Compliance with codes reduces the risk of fires and shocks. It also ensures the long-term reliability of electrical systems. Violations of electrical codes can result in penalties. Fines, project delays, and legal action are possible. To ensure compliance, use qualified electricians. Licensed electricians are trained in code requirements. Obtain necessary permits before starting work. Inspections are required to verify compliance. Stay up to date with code changes and updates. Codes are regularly revised to reflect new technologies. Implement a comprehensive compliance program. This program should include training, audits, and documentation. Compliance is not just a legal requirement, it is also a moral obligation to protect people. By prioritizing code compliance, you demonstrate a commitment to safety. You also contribute to a safer community. Safety risks must be minimized in electrical systems. High voltage and current pose significant dangers. Follow all safety procedures and guidelines. Always de-energize equipment before working on it. Use lockout-tagout procedures to prevent accidental energization. Wear appropriate personal protective equipment, PPE. PPE includes gloves, eye protection, and arc flash suits. Maintain a safe distance from energized equipment. Never touch bare wires or conductors. Inspect equipment regularly for damage or wear. Damaged equipment can be hazardous. Provide comprehensive safety training to all personnel. Training should cover hazard identification and safe work practices. Establish clear communication protocols. Effective communication is essential during electrical work. Conduct regular safety audits to identify potential hazards. Address any identified hazards promptly. Report any safety concerns immediately. Don't ignore potential problems. Promote a strong safety culture within the organization. A strong safety culture encourages safe behavior. By minimizing safety risks, you protect lives and prevent accidents. Safety is always a top priority in electrical work. Never compromise safety for convenience or speed. A non-invasive device does not require physical contact. This provides numerous advantages in various applications. Measurement without interruption is a key benefit. Processes continue without downtime or disruption. Installation is often simpler and faster. Non-invasive methods eliminate the need for connections. Risk of contamination is reduced significantly. Contact-based methods can introduce contaminants. Damage to the object being measured is minimized. Non-invasive techniques are gentle and non-destructive. Remote monitoring becomes feasible with ease. Data can be collected from a distance, enhancing safety. Versatility is a hallmark of non-invasive devices. They can be used in diverse environments and industries. Accuracy is maintained without physical interference. Measurements remain reliable and consistent. Cost savings can be substantial over time. Reduced installation, maintenance, and downtime contribute. Examples include thermal imaging and laser scanning. These technologies provide valuable insights without contact. Non-invasive devices play a crucial role in modern technology. They offer safety, efficiency, and accuracy. Overloads are dangerous conditions in electrical systems. They occur when current exceeds the conductor's capacity. Overloads can cause overheating and insulation damage. This can lead to fires and equipment failure. Protection devices prevent overloads. Circuit breakers and fuses interrupt excessive current. Regular inspections can identify potential overloads. Look for signs of overheating or damaged wiring. Proper wiring and circuit design prevent overloads. Use the correct wire gauge for the expected current. Avoid overloading circuits with too many devices. Monitor equipment performance for signs of stress. Unusual noises or smells can indicate an overload. Install surge protection devices to protect against voltage spikes. Surges can contribute to overloads. Educate users about the dangers of overloads. Encourage responsible use of electrical equipment. Immediate action is necessary if an overload occurs. Shut off the affected circuit and investigate the cause. Overloads are a serious threat to electrical safety. Prevention and prompt action are essential. Transient voltages are short-duration voltage spikes. They can damage sensitive electronic equipment. Lightning strikes and switching events cause transients. Surge protection devices, SPDs, mitigate transients. SPD divert excess voltage to ground. SPD come in various types and ratings. Choose SPD appropriate for the application. Install SPD at the service entrance and branch circuit. Multi-layer protection is recommended. Regularly inspect SPD for damage or wear. Replace SPD that have been exposed to surges. Grounding is essential for effective surge protection. Proper grounding provides a path for diverted current. Educate users about the importance of surge protection. Encourage the use of SPD to protect valuable electronics. Transient voltages are a common threat to electrical systems. Proper surge protection is a critical safeguard. Harmonics are distortions in the electrical waveform. They can cause various problems in electrical systems. Equipment overheating is a common consequence. Harmonics increase current flow, leading to heat. Reduced equipment lifespan results from harmonic stress. Harmonics shorten the life of motors and transformers. Inaccurate metering can occur due to harmonics. Traditional meters may not accurately measure distorted waveforms. Increased energy losses can be attributed to harmonics. Harmonics increase the overall energy consumption. Resonance can amplify harmonics, causing severe problems. Resonance occurs when harmonic frequencies match system frequencies. Harmonic filters mitigate harmonic distortion. Filters block or redirect harmonic currents. Regular power quality audits identify harmonic issues. Audits assess the level of harmonic distortion. Proper grounding and wiring minimize harmonics. Good grounding reduces harmonic currents. Educate users about the effects of harmonics. Encourage the use of harmonic mitigation techniques. Harmonics are a significant concern in modern electrical systems. Mitigation strategies are essential for reliable operation. When working with high voltage, extreme caution is important.